Hi. I wanted to do one of these types of problems where you find the interval of convergence for, this is called the power series, because there's a lot going on here. I want you to see how we treat the x versus how we treat the n. And then I want to show you my method of doing the ratio test, which for me at least makes it easier. So we are going to use a ratio test as you do with all of these things. And hopefully you've done a couple ratio tests by now. If you haven't, go back and try a couple and come back to this one because I'm not going to show you every single one of my steps. So you know that from the ratio test, it turns into, okay, so it's going to be -1 to the n plus 1 times x to the 2 times n plus 1 over 2 to the n plus 1 times n plus 1. So you might be saying, where's the absolute values and where's the limit? This is how I do it. I deal with the ratio first and clean all that up and simplify it because that's algebra and that's the fun, easy part. Then I deal with the absolute values. And then finally at the very end, I deal with the limit. And every one of these is a little bit different, but if you do it this way, I think it makes it just more comprehensible. So you know that dividing by a fraction is the same as multiplying by the reciprocal. So it always turns into this. So then it's going to be, 2 to the n times n over x to the 2n plus 1 times -1 to the n. So the second term in the ratio test is always just the original expression flipped upside down. Okay, so now I like to group all the like stuff with the like stuff. So we have a -1 to the n plus 1 up top, and we have a -1 to the n in the denominator. Then we've got an x to the, okay, quick little bit of algebra. 2n plus 2 plus 1 is 2n plus 3. We've also got, well, let's just get the whole numerator, a 2 to the n and an n. And now, okay, downstairs we got an x to the 2n plus 1. We got a 2 to the n plus 1. And we got an n plus 1. So in one fell swoop, I lined everything up and just put it into one fraction. Now we deal with everything kind of one at a time. -1 to the n plus 1 over -1 to the n. Well, that just leaves one factor of -1 up here. So let's just put it as a negative. And then we've got an x to the 2n plus 3 over an x to the 2n plus 1. So we subtract those exponents. 2n plus 3 minus 2n plus 1 is 2. So the only thing that survives that is an x squared up in the numerator, right? Because this is 2 more than this. Okay, so similarly, we got a 2 to the n plus 1 down here. We've got a 2 to the n up here. So the only thing that survives that process, we've got one more factor of 2 in the denominator than we do in the numerator. Okay, so it hangs around. And then we've got an n and an n plus 1, which we don't really know what to do with yet, but we certainly will. All right, so that's the first part of the ratio test. Like I said, now I'm going to slap the absolute values on it and see what that turns into. Okay, so the first thing that happens is when you put the absolute values around it, the negative, well, it just kind of goes away because the whole thing becomes positive. So that's the same thing as saying just positive x squared to the n over 2 to the n plus 1. And this is the part that's tricky because it's less like algebra and more about just kind of logic. Like the absolute value of something negative is the same as the absolute value of its positive counterpart. That's kind of what absolute value is, right? So it just makes the negative go away. And what you'll see is every time, so this is an alternating power series. Every time you do one of these, an alternating power series, it really doesn't matter which term is negative and which term is positive or whatever. When you get to this part of the ratio test, the negative just goes away. And you don't even have to explain it. Just make it go away. The next part you have to explain. So let's think about the absolute value of x squared. Well, x squared is always, we'll say non-negative. And why is that? Well, it just is. Anytime you square a number, it becomes positive, right? Nothing, you can't square a number and it becomes a negative number. That's imaginary, literally. You ever think about the graph of x squared? It can be 0 technically, but it could never be negative. So all that is to say, the absolute values don't do anything to that either. They don't affect the x squared. And then n is always positive. For a completely different reason. The reason that n is always positive is because it just is. It's the index of a series. So it starts at 1 and goes up from there. It's never 0 and it's never negative. Okay, so you can just say that, right? And that's what I mean. It's more like just kind of thinking about it. So all that is to say that if something's always positive, everything in here is positive. The x squared, the n, 2 is obviously positive. It's just a constant, the n plus 1. So when you put absolute values around something that's just positive no matter what, they don't do anything. So in this case, and again, not always, but in this case, you just forget about them. You just drop them. Okay? Okay. And then the next part, we haven't even finished the ratio test. We have to look at the limit as n goes to infinity of this expression. So that's just the first part of the ratio test. We dealt with the actual ratio, simplified as much as we can, and then we dealt with the absolute value bars, and they're just straight up not going to be there. Okay, so now we get to the next part where we actually have to look at the limit, and I wanted you to see how to deal with that. So now we have to calculate the limit as n goes to infinity of x squared times n over 2 times n plus 1. So the only thing this limit is affecting is the stuff with an n in it. The x squared is not affected by the n. The 2 is not affected by the n. So one of your old kind of algebra laws for limits was that anything that's not affected by the limit can come out front. It doesn't have to, but it can, because it doesn't care that n is going to infinity. So x, you really just treat x like a constant for this whole first part. Just treat x as if it were a constant. Now x, as we know, can be anything, or we're figuring out what it can be. But either way, as far as the limit goes, it doesn't matter. So now I don't know how you think about this, but this limit is 1. Okay, I can explain that further if you need me to, but you maybe should be able to just look at it and know that it's 1 because these n's are the same power. So this whole thing is just x squared over 2. Okay, so that's just the part of it where we apply the ratio test. Now remember what the ratio test says. We did all this work because we require this. So this whole series converges if this limit of the absolute value of the ratio of the terms is strictly less than 1. And this algebra is even a little bit weird too. So for starters, just multiply both sides by 2. When you're dealing with inequalities, it's also kind of like you just kind of think about it. So think about the graph of x squared. To me, this is like a polynomial inequality equation. That's a really crappy parabola. It touches there. Okay, good enough. For x squared to be less than 2, so x squared is never negative, but if x squared were anywhere between here and here, then x squared would be strictly less than 2. So just see if you agree with me here. If x were strictly between negative square root of 2 and positive square root of 2, this would be true. So if you're wondering where that answer came from, that's where it came from. But again, it's weird because you're not just square rooting both sides. You have to think about it. And to me, the easiest way to think about it is just to picture the graph of x squared. How could x squared be possibly be less than 2? It can be negative, but if x were anywhere between the negative square root and the positive square root, right? If this were an equation, you would just square root both sides. And include a little plus or minus. So it's an inequality, so it's similar. Okay, so we're not even done. So that's what we call the interval of convergence, but we don't know what happens at the endpoints. And this is the part, it seems really finicky, but we put it in anyways because endpoints are important. And the whole point of this is to find the domain of a function. So like it matters whether or not it works here and here. And I think I'll just do one of them and the other one works out exactly the same. So you just test them. You just plug them in. So I don't even remember. What was the original thing? You just plug it into the original thing. So it's the sum of negative 1 to the n times x to the 2n plus 1. So that's square root of 2 to the 2n plus 1 over 2 to the n times n. And we have to clean that up. And then use one of our tests to see if it converges. So, right, these aren't quick. Okay, well, everything else is just kind of whatever. So this is negative 1 to the n. Here's how I deal with this. I say the square root of 2 to the 2n plus 1 is the same thing as the square root of 2 to the 2n times square root of 2 to the 1. Agree with me there? That's just how exponent rules work. So I chose to split it up into two things because now it's easier to see what happens. Okay, so the square root of 2 to the 2n, again, this is a lot going on. Okay, it's okay to not be okay with this. Square root of 2 squared to the n. And then square root of 2 to the 1 is just square root of 2. And then I'm going to go up here. Square root of 2 squared is just 2. The reason I would like to break it up that way, okay, square root of 2 squared is just 2, and then that whole thing is 2 to the n. We're getting there. We're close, I promise. All right, so just general series function-y stuff. The square root of 2 is a constant. It doesn't affect anything. So it can actually come out front. Well, it does affect things, but it's just being multiplied into every single term, all infinity terms in the series. So it's almost just factoring. You can just factor it out front and ignore it. If a series converges, then the square root of 2 times the series also converges. Think about that one. Okay, so we have a 2 to the n times, or over 2 to the n, so we love that. That factors out. So it's just negative 1 to the n times 1 over n. Okay, so at its endpoint of its interval of convergence, the series is that series, which is an alternating series which converges, because all you require for an alternating series to converge is for the limit of its terms in absolute value to be 0. Remember that? Okay, so you essentially ignore the negative 1. As long as 1 over n goes to 0 and it's alternating, the entire series will converge. So it converges by, I should specify, that was the alternating series test that I used. You could also say that 1 over n is a p-series with p equals 1. Now, if the negative 1 weren't there, it wouldn't converge. Remember that? This is actually specifically called the alternating harmonic series. So the regular harmonic series does not converge, but the alternating harmonic series does converge, because all that we require for alternating series to converge is that the limit of the individual terms in absolute value, ignoring the negative 1, converges to 0. Okay, so all that work was just to say that we can put a little or equal to here, because square root of 2 is included in the interval of convergence. Now just picture this, if you will. Plug negative square root of 2 into this thing instead. The second we square it, the negative goes away. So you could do all this work again, or you can just kind of trust that fact. It's going to work out exactly the same way, because if you have negative square root of 2 to the 2n, then it's just going to be negative square root of 2 squared to the n, and the negative becomes a positive. So all that is to say that in your final answer, what the heck were we doing in the first place? We're trying to find what's fancily called the interval of convergence. Both of these endpoints are included. Or you could simply write it like I think it is on the answer sheet. All right, so the radius of convergence is square root of 2. If you haven't heard, comment. me off. If you haven't heard the term radius convergence yet, don't worry about it. But either way, that's the interval of convergence. Okay, so that is the domain of that power series. Okay, these are a lot of work and they are hard. Thank you.